Okay, boys and girls, here we have the notes for section 5, the multiplication rule, part 2, essentially, complements and conditional. So complements, this normally happens when you see the probability of at least one. So it says here, when finding the probability of some event occurring at least once, it is usually best to solve the problem backwards by working directly with the complement. At least one has the same meaning as one or more. Now the complement is that you get none. Now the reason this works, if I need to find the probability, if I have a bunch of events, if I wanted to have the probability of finding at least one of something, that means I have to find the likelihood of getting 1, and getting 2, and getting 3, and getting 4, and getting 5, and so on and so forth until I have all of them, and I have to add all those probabilities up. However, it's easier to find the probability of it not happening because there's only one way that could occur. I get 0 of them, and then I subtract that from 1 because the complement is the remainder part of it. So down here you have the steps. So let A probably get at least 1, then A with a bar, so the opposite of A is getting none, because at least 1 covers every other possibility, 1 and up, so none is the only thing that hasn't been covered. So then you find the likelihood of getting none, and you subtract that result from 1, because that'll get you return back to this. So if you think about it, where am I going to write this? Put over here. So the probabilities of an event occurring, you get none of them, or you get 1 of them, or you get 2 of them, or you get so on and so forth forever. So if I want the probability of at least 1, I can either add up all of those probabilities, or I can find just that one probability, because the total of all of them has to be 1. So I can do this one of two ways. 1 minus this guy is the same as all of these added up. So instead of having to do all those addition steps, I just find one probability and subtract it from 1. So down here, top for blah, 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 lots of 50, defective rate of 0.5%. So the probability is off the screen, 0.005. It follows the probability of a disk being good is 0.995, 1 minus that number. If an engineer wants to carefully analyze a defective disk, what's the probability of her getting at least one defective disk in the lot of 50? Is the probability high enough that the engineer can be reasonably sure of getting a defective disk that can be used? So instead of finding the probability of getting 1 and 2 and 3 and 4 and 5 and 6, I'm going to find the probability of getting none of them. So that means that getting no defectives is the same thing as all good, off the screen again, disks. So that means I need to find the probability of all the disks being good. So this essentially is P0, no defective, is 0.995, the likelihood that the disk is good, to the 50th power. So there's 50 disks to check. So 0.995 raised to the 50th is 0.778. So at least one defective is going to be 1 minus the likelihood that none of them are defective. So 1 minus 0.778. I should be able to do this in my head. Is 0.222. So that's almost a quarter of the disk, but she has a 25% chance. So yeah, she's got a pretty good chance of finding at least one defective disk in her batch of 50. Okay, next we've got conditional probability. So the conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. So that's written as P bar A, of event B occurring given that A has already happened. So what's the likelihood that, what's a good one? If you know it's Sunday, there'll be football played. Or, if it's a day of the week, it is a work day. Or, sorry, that's a bad example. Music conditional, it doesn't work there. So this is the fancy math version of doing it. There is a much more intuitive way, especially if you have the data, and that's where you ignore the parts that don't matter. So essentially, if you look down here at example 2, if one of the 1,000 test subjects is randomly selected, find the probability that the subject has a positive test result, given that the subject actually uses drugs. So what I'm going to do is, since I know that the subject uses drugs, I can ignore these two values. They're not going to be included. I'm just looking at the top row. because I know that the subject uses drugs. So my bottom number, instead of being out of the 1,000, is only out of the 50, because I only need to look at the 50 people who I know use drugs. The positive test result would be the 44, because they're the people who use drugs and test positive. So 44 out of 50, which would be 22 out of 25, which as a decimal is 0.88. So down here, so this is the reverse of or if one of the 1,000 test subjects is randomly selected, find the probability that the subject actually uses drugs given that they have a positive test result. So my given goes on the bottom. So that's just these two values added together. I know they have a positive, I know they have a positive result. So my denominator has to be 134. Do they use drugs is the top number again. So it's 44. So I know they had a positive result. So 44 plus 90. How many of them actually use drugs is the top row value here. So 44 out of 134 is 22 out of 67, or as a decimal, 0.328 is a probability. It does keep going, but we usually go to 3 places for the probabilities. So there you go. So if you notice, these aren't the same number. So the conditionals, even though they use the same things, positive test results and subject using drugs, positive test result, subject using drugs, the order matters. They won't be equal to each other. And that's actually what the last example here deals with, because now we start section 6. This is referred to as a confusion of the inverse, where the order does matter. So it says, consider the probability that it's dark outside, given that it is midnight. So probability that it's dark, if you know it's midnight, is 1. We're ignoring like Alaska in the middle of summer, things like that, where the sun doesn't actually set. But usually, almost always, if it's midnight, you know it's dark, guaranteed. Probability is 1. Over here was the probability of the inverse, that if it is dark, you know that it's midnight. Well, this, given that it's dark, is essentially 0, because there's lots of other times that are not midnight when it is dark. So you cannot make that assumption. You can't look outside, see that it's dark, say it's midnight. You almost always will be wrong. There's only one exact time in which you are correct, and that's when it's exactly midnight. So this number might as well be 0. So be careful with the order. Pay attention to what comes second. That tells you your category you're looking at. The thing that comes before the bar is which part of that category you are looking at. That wraps up this section.